That's all I speak about these days, complexity. This is probably going to end my career, both because I'm 80 years old, and secondly, because at some point somebody's going to say, let's stop hearing about complexity. Okay, complexity is very hard. It's really hard. It's much harder than entanglement. But my own opinion is that it's every bit as important to quantum gravity and black holes. So we'd like to find an easier way to visualize it. One hope was to follow Michael Nielsen's idea of a complexity geometry, take the space of states or the space of unitary operators or whatever it is we're interested in, and give it some sort of non-standard metric. Non-standard metric which represents the difficulty of going from one point to another by acting with some restricted class of operations. This, in mathematical terms, means a right invariant metric. For example, on the space SU2 to the n, which is the space of not the space of unitary operators of n qubits, equipped with some appropriate penalty factors for moving in hard directions. But as you might expect, the geometry that you get in this way is also extremely difficult and hard to understand. Incidentally, if it were easy to understand, we would use it and solve all complexity problems. Well, we're not going to solve all complexity problems, and so the geometry itself is very hard to think about. In lieu of that, what we would like to do is to find some very simplified model. Simplified model that makes it easy to analyze, but still captures the basic things that we think complexity should do. I won't justify it in this talk, but there is a simplified toy version of complexity geometry, and it's nothing but the hyperbolic plane, the hyperbolic disk, where the center of the disk represents the unit operator, and points away from the disk represent unitary operators of larger complexity. The further away you go from the center of the disk, the more complex the operator is. There are two ways to think about the relative complexity, ours, relative complexity. If I have two unitary operators, I can ask how many gates does it take to go from one to the other by operating, let's say, by left multiplication, and that minimal number of gates to go from one to the other is called the relative complexity. And you can think of it in two ways. You can think of it 2 points on the hyperbolic plane or on the complexity geometry. The way Nielsen thought about it was as the geodesic distance between the points, the relative complexity. The way I like to think about it, which is completely equivalent, is to imagine a non-relativistic particle moving on the geometry and think about the minimal action for the particle to go from one point to another. They're completely consistent with each other. The action point of view suggests something which turns out to be true. It suggests that if you're thinking about an ensemble of theories, like in SYK, you can start out with a whole bunch of points at the origin to follow the complexity and let them flow away by the natural dynamics induced by the metric of the space. Let them flow away, and the complexity just turns out to be the entropy of that cloud of particles. As the cloud of particles expands, the entropy grows, and the entropy, or the average, and the entropy grows, and that entropy is in fact the average complexity of the points that the cloud is covering. So that turned out to be a somewhat easy way to think about complexity, and I will use it. One of the outcomes of this view is that there's a second law of complexity. I'm told now that there's a first law of complexity, is that right? Okay, I didn't know that. The second law just means, very simply, that there's a kind of pressure on systems or a kind of force on systems to push them toward larger complexity. In the same way, or a similar way to the way there's a force that pushes systems to larger entropy. What I'm going to tell you today is that that force is nothing but ordinary gravity. So that's what we're going to do today. Another preliminary. One other preliminary is what I call the momentum size correspondence. This is not as well known as it should be. It's been going on for some 50 years now, mostly in my own writings. I've listed here some history of the subject. I'll say it as simply and as quickly as I can. In a quantum field theory, a particle has a fixed size, which in this context means number of constituent elementary particles. For example, a proton has 3 quarks. And whether the proton is going fast or going slow, it always has 3 quarks. Now, that's not exactly true. Those who know about deep inelastic scattering and so forth know about something called the wee-parton effect and so forth. That says the number of particles that you will see in a proton does depend on its energy, but gradually, logarithmically. In gravity, by contrast, you could say it a number of ways. You could say all partons are wee. Or you can just say the number of partons in a particle grows with its momentum in such, and the number of partons, I'll give the name the size of the particle. The size of the particle, or the size of the object, grows with momentum. That's a shocking idea because it seems to violate Lorentz invariance. If you ask me about it later, I'll tell you why it doesn't. And in particular, as I said, the number of constituents can be identified with what we tend to call size in SYK kind of theories and so forth, and we'll come to that. So, momentum is proportional to size, and of course momentum has units, 1 over length. Size is dimensionless, so there has to be a factor connecting them. The factor has to have units of length, and I'll call it beta. Now, you say, well, beta we already use for inverse temperature. Yes, we'll come to it in a moment, but for the moment, it's just a conversion factor from size to momentum. All right, now how are we going to examine this? We're going to examine this in a particular theory, everybody's favorite theory today, SYK, and it's bulk dual. And I'll take its bulk dual to be a near-extremal Reisner-Nordstrom black hole. You can call it JT gravity. JT gravity is basically the dimensional reduction of the near-extremal black hole. I like to think about it in the near-extremal black hole just because I'm familiar with it. Okay, near-extremal black hole is just a long throat. It's a long throat which at one end has a horizon. The other end opens up into asymptotic space. And in fact, there's a fairly sharp transition between the two. The sharp transition happens at a point where there's a potential barrier that particles from the inside experience when they try to get out, and particles from the outside experience when they try to get in. And it makes a sharp dynamical boundary between the inside and the outside. And if you like, you can try to cut off the geometry and replace the outside by a boundary condition or a boundary term in the action. That boundary term in the action is the York term, sometimes called the Gibbons-Hawking York term. I'm not sure why. It was definitely York who invented it. And as I said, it's called the Gibbons-Hawking York term. It's a term in the action. Just remind you of that. And there's a dictionary connecting SYK to the near-extremal black hole. I'll tell you what it is very quickly. The horizon size, the horizon radius, I'll call R plus, the outer horizon, but for the near-extremal, the outer and the inner are almost the same. And the inverse of that is the SYK energy scale, J. The entropy of the black hole, which is basically the area of this tube, is N, the N of SYK. There's N times a number. The number depends on little q. Don't worry about it if you don't know what that is. But it's basically just N. And if you know the radius of the horizon, you can compute its area. If you know the entropy, you can compute the Newton constant. And the Newton constant, I'm talking about the 4-dimensional Newton constant now. G is 1 over J squared N. And the mass of the black hole, the ordinary mass of the black hole, is N times J. And finally, the York-Gibbons-Hawking action associated with the boundary is just the Schwarzian action that we've become familiar with in recent times. Okay, now we're going to apply a perturbation W at the boundary. Perturbation, what could it be? Just some operator, a simple operator, and the simplest thing would be a single fermion in SYK, single fermion operator. And that'll create a particle. The particle will, what will it do? It'll fall into the black hole. It'll accelerate as it goes down due to the gravitational attraction. And that's what we're interested in. We're interested in understanding the reason for that gravitational attraction. We can go to the SYK. This has got nothing to do, obviously, with gravity. It's pure quantum mechanics. And we can study what the evolution of that perturbation is. The perturbation is generated by an operator, W. W evolves with time. And the time evolution has an effect which we've found out by various calculations is that the perturbation grows in size. And it grows in size in a particular way, in a tree-like way. By tree-like, I don't necessarily mean that the diagrams have no loops. I mean that it proliferates exponentially. This is just a simple toy example here where it grows like a, I suppose it's a sort of sideways, what do the Jewish people call it, a menorah. Yeah, but I would think of it as a tree. And it grows exponentially. Exponentially with what, incidentally? Time. Not necessarily time, but with depth of the circuit, number of layers. Is the number of layers proportional to the time? We'll come to that in a moment. But the size at any given time is the number of leaves of the tree. Number of leaves of the tree means the number of endpoints. The complexity of the growing operator can be identified with the number of vertices. You can think of the vertices as gates, the number of steps that it took to get there, and the complexity I'll think of as the number of vertices in the diagram. They grow together, and in fact, because it grows exponentially, well, first of all, you can see from the picture that the size is proportional to the derivative of complexity. That's just every time you add a layer of complexity, you add one layer of complexity adds to the size. And so one equation that we use is that the size is the complexity dt. But the other thing is that because it's growing, incidentally, it only grows exponentially until the scrambling time. At the scrambling time, it saturates. But up to the scrambling time, because it grows exponentially, the size and the complexity are proportional to each other. So I'm going to simply use the letter C for both size and complexity because everything we're going to say is in this pre-scrambling time. Okay, now, is the parameter tau time? No, in general it's not. You can imagine a variable rate computer where the computer is just doing its usual thing, but at a variable rate. Why would the computer, this particle falling into the black hole and evolving according to these computations, why would it be a variable rate? Two reasons. First of all, because it's falling into a potential well with time, what did Einstein call it? Time dilation? Right. Sorry? I think it's called time dilation. Yeah, I just didn't want to confuse it with Lorentz dilation. It's redshift. Thank you. That's the word I was looking for. But also because it's going faster and faster as it goes down there, it also has some Lorentz time dilation. So there's a variable rate, as seen from infinity, there's a variable rate. And if the size is the complexity dt, as I argued before, sorry, the complexity d tau, with tau being circuit depth, then we have to introduce this factor beta tilde. I'll tell you what beta tilde is in a minute, but it's basically the rate parameter or the inverse rate that the computer is computing with. That beta tilde turns out to be, from direct calculations, I won't do the calculations here, but it turns out to be an interesting thing. As the system moves down through the throat, it comes to different places, and that beta tilde is the inverse temperature of a black hole whose horizon was right at the position that we're talking about. So as something moves down that throat, it experiences different places, and that rate is the temperature of a black hole whose horizon was up at the point in question. You'll have to take it from me that that's true. We can call it the inverse energy scale. And so we have an equation, size is equal to beta tilde dc dt, t being asymptotic time.